All right, so this is a demonstration of the Thompson Experiment, which was an experiment around the turn of the century, the 1800s into the 1900s, the beginning of the 20th century, where the principle was looking at what happens to this beam of light created by a cathode when we expose it to magnetic fields. The idea of this cathode is the same as a cathode ray tube, where we're applying a voltage to the cathode and it's shooting electrons from the cathode in a straight line. As we do that, those cathodes are colliding with helium atoms that fill up the inside of this bulb, and when it hits the helium atoms, it excites the electrons in the atoms, which causes them to go to a higher energy level, and then when they fall back down to their ground state, they emit light. So you can't actually see the electrons when you look at this. Instead, you're just seeing a trail of light left by the electrons colliding with the gas atoms. But it does show us the path that the electrons are taking. So for this experiment, we control the voltage using this voltage source. It's currently set to 120 volts. By doing some math, we could calculate, based on the voltage, the speed that the electrons are being launched out of the cathode. Around here, we have two Helmholtz coils, which are coils of copper wire that are wound in opposite directions, so that when we charge them up, when we run a current through the coils, it's going to create a uniform magnetic field. Since the electrons are charged particles, when we have electrons moving through a magnetic field, there's going to be a force on the electrons. You could use the right-hand rule to figure out what direction that force would be. And so based on the speed of the electrons being in one direction and the magnetic field pointing in another direction, whether it's towards the camera or towards me, it'll apply a force on the electrons that will cause them to curl. I'm going to go ahead and I'm going to turn the lights off so that you can see the beam, and then I'll start to increase the current through the coils to create that magnetic field. So right now you can see the beam traveling in a straight line, and as I energize our coils, you can see the beam start to curl. The more current that we run through the coils, the stronger the magnetic field will be. And the stronger the magnetic field is, the more force the stream of electrons experiences, and so the more it curls, until eventually it curls in a full circle. So for this experiment, when Thompson was doing it, what he did is he controlled the voltage to control how fast the electrons were being ejected from the cathode, and he controlled the current in the coils to control how strong the magnetic field was, until he bent the beam of electrons into a circle. Then, by doing some math that we aren't going to do here, he was able to calculate for these particles what is the charge over mass ratio. And he was able to show that no matter what material, all materials seem to have these particles which were always the same charge over mass ratio, which was one of the key steps in proving that the electrons are a fundamental particle that we can find all throughout matter. One of the interesting things that we could also show with this, right now we see it making a nice, neat circle, but if we turn this, that circle will actually become a spiral because it's just slightly off axis, and so the magnetic field is pushing, and instead of just going in a perfect circle, it now becomes a spiral that either spirals towards you or towards me. And this is a demonstration of the Thompson experiment that showed the charge over mass ratio for an electron.